Good afternoon. Welcome. We're it's our last lab, and it's very timely with what we're covering in lecture. I haven't gotten to all the concepts that we're covering today, so I'm going to kind of uncover them as we go through the lab. Are there any questions before I begin? Feel free to interrupt me as I go. Let's look at the lab. All right, so what's the T? I don't know what the T, theory, the theory. Usually they don't have the T in there. We're going to look at molecular shapes, and molecular shapes are governed by this theory called VSEPR. It's a very simple theory, and so it kind of goes hand in hand with Lewis structures. So we're going to review Lewis structures, and then the thing about Lewis, however, is Lewis just tells you the bonding, how the attachment is. For instance, maybe I should go to, I'm going to go to a whiteboard. So according to Lewis theory, Lewis dot structures, right, we can tell the bonding between, let's go, I'm actually going to go through it step by step. Let's look at Lewis dot theory or Lewis dot structures. It's very simple. It's a very simple model, and it's pretty accurate. So it's a very simple model. It's pretty accurate. And so I think I did this in lecture, but there are rules for writing Lewis dot structures. And sometimes you don't need the rules, but using the rules I think helps every time. And so for the rules, you write the skeletal structure. That just means arranging the atoms together. Where you like what you think is going to be in the middle, what you're going to think going to be on the end, how the bonding is going to occur. You kind of arrange them. How do you think they're bonded? And you kind of use common sense. Like, so the atom that forms the most bonds will be more in the center, right? That's a good rule. And the ones that don't form many bonds, like hydrogen and like fluorine or chlorine, they would be on the ends. So you write the skeletal structure, and then you count the total valence electrons. And then you make single bonds. And then you complete octets. Complete octets with lone pairs. And then finally, if you cannot complete all the octets, like if you're short a couple of electrons, you're completing the octets and you run out of electrons, right? Because the number of valence electrons, this will tell you how many electrons that you can use. So these are all the electrons that you can use, or the valence electrons. And so after you make the single bonds, right, you're using up 2 electrons for each single bond. And then you complete the octets with lone pairs, right? So you're using like 2 electrons for each lone pair. And so you want everything to have 8 electrons around it, of course, except for hydrogen. So complete octets with lone pairs. And if you need more electrons, if you run out of electrons, you're making lone, and everything doesn't have an octet, make a double bond. If you need 2 more electrons. And so if you're 2 electrons short, you make a double bond, right? If you're 4 electrons short, you can make 2 double bonds or a triple bond. And so let's apply these rules to a very simple structure. We'll do the structure for H2O. And so I'm going to put oxygen in the middle. I think we already know the structure of this, right? But we'll do it with the rules. So there's my skeletal structure. A lot of times it's good to go to symmetry, right? So, and then count the total valence electrons. Oxygen has 6 and 2 hydrogens is 2. So we have 8 valence electrons. And so I'm going to make the single bonds. That's 2, 4. Then I complete the octets. And there's my structure for water. Right? So oxygen has an octet, 2, 4, 6, 8. I used all the electrons. Everything's happy. Hydrogen has 2. Hydrogen has 2. So this is a good structure. What Lewis doesn't tell us the shape of water, right? Is water linear? Is water kind of bent, like at a 90-degree angle like this? Right? So what is the shape of water? So according to Lewis, both of these structures are acceptable. Both of these structures are acceptable. And so to tell us the shape of the molecule, what shape the molecule takes on, we're going to use valence shell electron pair, because electrons come in pairs. They're either lone pairs or bonding pairs, right? You have a lone pair or a bonding pair. So valence shell electron pair. And what do electrons do? Electrons, they have the same charge. And so they're going to repel one another. They want to be as far away from each other. So the electrons have the same charge, so they repel, right? So valence shell electron pair repulsion. And just by the fact that we know that VSEPR, that's what they call it VSEPR, just by the fact that electrons repel one another, it allows us to determine the shape. It allows us to determine the shape of the molecule. And so let's go with a very simple molecule, something like, so let's look at these structures, and we'll start with a very simple molecule. And I haven't taught in lecture yet, but there are something called octet rule violators. There are a couple of octet rule violators. And so typically your octet rule violators, you're going to have your beryllium and your boron and aluminum, I think, will be an octet rule violator for the most part. We could leave the boron, I will leave it in, but it's pretty much is beryllium and boron. So these will have too few. And so if I do the Lewis dot structure, beryllium will take on a structure of beryllium hydride. And so if we do beryllium hydride, do the Lewis dot structure, you'll find that if you go through the rules, here's my skeletal, I guess I'll go through it. Here's my skeletal, how many valence electrons? Beryllium has 2. 2 hydrogens is 2. And so that's 4 valence electrons, right? So you could just make 2 bonds. There's no electrons to make, you can't do anything else. There's no lone pairs to make a double bond. And so beryllium is an octet rule violator. It's kind of happy with just 4 electrons around it. So this is an octet rule violator. But if we look at the shape of this thing, so looking at the shape of this, those electron pairs right here, those electron pairs in that very long bond there, and those electron pairs, they want to be as far away from each other as possible, right? So these bonding electrons want to be as far apart as possible because they repel, as they want to be as far apart as possible. And so they're going to take on a shape. And when we talk about we're going to talk about 2 different things. We'll talk about the electron geometry and the molecular shape. And so the electron geometry is based on the number of groups. So electron geometry is based on number of electron domains. They call them electron domains. or that's an R, groups. And so here we'll see that. And so let me define electron domains or groups. So it's either like a bonding domain, or I'll use that word, bonding domain, or a lone pair. So both of these count as groups. So it's either a bonding domain or a lone pair. That's that, and that'll determine electron geometry. And so here we have beryllium dihydride, and there are two electron domains, right? And they're both bonding domains. And so those bonding domains, they want to get as far away from each other as possible. And how do they achieve that? And another thing I need to say is that we're always referring to around a central atom. So when we're talking about the electron geometry, it's always going to be around a central atom, right? There always has to be an atom in the center, right? To come up with these bonding domains, right? It really doesn't make sense to talk about the geometry of, say, oxygen, right? It really doesn't make sense because there's not really a central atom, right? There's one over here, there's nothing in the center. There's no central atom. But you can talk about the geometry of ozone, right? You can talk about the geometry of ozone, right? Because there's a central atom. And so when figuring out these electron geometries and these molecular shapes or molecular geometries, we're always talking about a central atom. We need a central atom. And so we only really care about the electron domains or groups that are on that central atom, right? And so I could write my ozone. I'm only showing you the lone pairs that are on a central atom. I'm not showing you these ones because I don't care about those, right? I'm trying to figure out the geometry. I only care about that central atom. And so when writing, so it's a little bit different going from Lewis structure to a three-dimensional structure. So we're going to go from a Lewis structure to a three-dimensional structure, and we're looking at the number of bonding domains around a central group. All right, so this beryllium here has two bonding domains, and they want to be as far away from each other as possible. How do they achieve that? Well, they've already, right? They can't get any further away than they are right here. And so what is the bonding angle? So this bond angle is 180 degrees. They cannot get any further away from that, right? So we can see that if you have two bonding domains, right? So there's going to be rules. If you have two bonding domains or two two electron domains, they're going to take 180 degree orientation. And so that will determine the shape. And so what is the electron geometry? The electron geometry for beryllium dihydride is linear. And the molecular shape is the same. It's both linear. And so what's the difference between electron geometry and molecular shape? Molecular shape, we're just looking at the atoms. So electron geometry, we're looking at the geometry that is achieved by all of the electron domains. So that would include lone pairs. But when we're looking at the shape, we're going to exclude the lone pairs. We're going to talk about the shape that the molecule took based on its electron geometry. Let's if we look at our book, so our book has a very nice model here. If we look at our book, I think I have it here. If you go to your book and the textbook, right? They talk about the chapter 7 talks about this, and then you click on the molecular shape simulator. It'll take you, so you click on molecular shape simulator, and it'll take you to this cool thing. You just hit play, like it says like download it or something. I think this image comes up, right? So I already have it up, but you could just hit play. Just hit play, and it'll take you to this thing right here. It'll take you to this. And this is pretty cool. And so you could do with real molecules or models. And so we'll start with models. And so this is like my beryllium hydride, if you will. And so we can click on electron geometry. What's the electron geometry of this? It's linear. What's the molecular geometry? It's linear. So they're the same. If you don't have lone pairs, the molecular geometry and the electron geometry will always be the same. And we can show bond angles. It's 180 degrees. So there we go. So there's our first geometry. If you have two groups, it's going to take an electron geometry of, wow, that's really, isn't that cool, right? So this actually will have like almost all the answers. I kind of, it's really good to learn from, right? And it's great since we don't have access, we're not in person, we're not touching and stuff, but this is a pretty good, it's a pretty good model. And so you can actually do this if you make balloons, if you blow up balloons and you keep them all like the same size, and then you attach them. If you attach two balloons at the center, you'll see that they'll take on a linear shape. If you add a balloon, you'll see it'll take on this trigonal planar shape. And so what does that mean? And so all these, they're in the same plane, right? It's still planar, and it's 120 degrees. So they got as far away from each other as possible. They take on the shape that's trigonal planar. So you can add or take away molecules. So let me go back to the board. And so this VSEPR theory is based upon the fact that the electron domains want to be as far away from each other as possible. All right, so I said that beryllium was an octet rule violator. Boron is also an octet rule violator. So let's go with my next example. Boron trifluoride. This is usually the classic example. And so boron is another octet rule violator. If we make it, I'm going to put boron in the center because fluorine only bonds to, so we'll go through it, put boron in the center. Fluorine has 7, right? It only bonds to one thing. And so this is how you do it. So this is, I like going through the rules to do it. So rule number 1, put them in order. Rule number 2, count the total valence electrons. Boron has 3 fluorines, that's 7 times 3, that's 21. So we have 24 valence electrons. And then you start making the single bonds. And then you complete the octets. And then you see, so we use 24 and boron only has 6, right? So boron only has 6 electrons. And so boron is an octet rule violator. So those are the common, is beryllium and boron are the common octet rule violators. They have too few. Too few. And so you might say, wait a minute, why don't we just make a double bond, right? Because I could just go like this. I can make this model. I could go boron, fluorine, right? You told me that if I have too few, I could just take a lone pair and make a double bond. Now everything has an octet. How don't we just go with this, right? Everything has an octet, and then we can see we have resonance structures, right? That seems like a better model, right? Why don't we just do that? And so we could see that that this is the better model if we employ formal charge, right? If we employ formal charge, look at the formal charge on this one. This is going to be 7 minus 7 equals 0. So that's good. And then 3 minus 3 equals 0. So everything has a 0 formal charge on this one, where boron is an octet rule violator. And if we do the formal charge over here, this is going to be 3 minus 4 equals minus 1. So you'd have a minus 1 on boron, which is kind of weird because fluorine is the most electronegative atom, right? And then this fluorine over here is going to be 7 minus 6 equals plus 1. And so this is just not a good formal charge. The most electronegative atom is going to have a plus 1, and boron, which is not very electronegative, has a minus 1. So that's why we see that this is the better structure. And so boron truly is an octet rule violator. In fact, if we react boron with ammonia, I don't know if you guys know ammonia, but ammonia has a pair of electrons, and so the ammonia will form an adduct with the boron, showing that this is like electron deficient. And so it's kind of, so boron reacts in such a way as to show that it truly is an octet rule violator, right? The pair of electrons are going to attack that boron. And so these are the octet rule violators. Beryllium is happy with just 4, and boron is happy with just 6. All right, but we're talking about the regardless of which Lewis structure we use, right? The one with the octets or the one with the violator, they're going to take on the same shape, right? Because in both of them there are 3 electron domains or groups. So whether you have a single bond or a double bond, it still counts as one bonding domain. So they would still take on the same shape, and we saw the shape already, right? So 3 bonding groups, 3 bonding domains. It'll take on a shape like this, right? So they can't get any further away than that. They cannot get any further away than that. And how far away is that? That's 120 degrees. Cool. Any questions? Right, and we saw this with our cool model. 120 degrees. Three bonds. All right. So let's see what happens. What happens if we add a lone pair? So let's do an example where we have a lone pair. So once you add a lone pair, the electron geometry and the molecular geometry are not going to be the same anymore. And so that's a good time to show this. So I'm going to stop share. I'm going to go back to my page. And so let's do an example of one where we have a lone pair. And so we'll do ozone. Right? We kind of touched on ozone already a little. O3. And so what do you put in the middle? We'll put oxygen in the middle. And then so I put oxygen in the middle. So the number of valence electrons is 3 oxygens is 18 valence electrons. So 18, so make the single bonds, complete the octets. I always start on the end for some reason. And then so I used all 18, so that's 8 and 16, 17, 18. But you can see the central one is short. So I need 2 more, right? Because I need to complete this octet. And so what am I going to do? I'm going to erase a pair of lone pairs and turn them into a double bond. So now everything has an octet, right? So 2, 4, 6, 8. You guys can't see my cursor? The left one has 8. The central one has 2, 4, 6, 8, and the other one has 8. And so now how many electron groups? So how many electron groups? Well, we have, this is one bonding domain, right? And this is another bonding domain. And then this is a lone pair. So lone pair and bonding domains. And so there are 3, right? So that means, so there's 2 bonding domains, 1 lone pair. So we have 3 electron groups or electron domains. And so we arrange them. We're going to arrange them. If we have 3 electron groups, they're going to take the same shape as that boron, right? Where we have we'll put the lone pair up. We could put the double bond oxygen this way, and the single bond oxygen over there. And so they're kind of, so there are 3 bonding domains. So the electron geometry is the same. It's trigonal planar. Trigonal planar. So, but the bond angles change a little bit. The bond angle are going to change a little bit because the lone pair requires a bit more space. So this guy, since he's so close to he's so close to this oxygen atom, he needs more space. And so what that does, that kind of it compresses this bond here. So these guys are forced closer together because the lone pair requires more space. Needs more space. And so we could just say that this is going to be less than 120 degrees. I think it goes down by like 1.5. So if you really want to be technical, it's probably like 118.5, but less than 120. It kind of shows me that you know what you're talking about, right? Less than 120. So the bond angle of this one, rather than being 120, it's going to be less than 120 because there's a lone pair. Now, what is the molecular shape or molecular geometry. Molecular shape or molecular geometry. Now we're just looking at the atoms, right? And so now these atoms, it kind of looks like a boomerang, doesn't it? Right? It kind of looks like a boomerang shape. And what do they call that shape? They don't call it boomerang, right? They call it bent. So ozone is bent. So here we see once we start to introduce lone pairs, it's kind of like a derivative of the electron geometry. So the molecular shape just looks at the atoms. And so let's check that out. We'll go to our cool model. And let's take away a bond and add a lone pair. There's a lone pair. It's not showing us, it's not optimizing the shape, right? It's not giving us the exact shape. I mean, it's not giving us the exact bond angles perfectly. Crazy. But if we shift to real models, right? But you can see that the molecular geometry is bent, right? The molecular geometry is bent. But now I want to show that this is not 120. That's idealized. So we'll go to real molecules. We're not going to do water. Is there no ozone? Oh my goodness. There's BF3. We did BF3, yeah. How is there no ozone? There's nothing like it. All right, we just have to go. We're going to have to move on. We're just going to have to move on. All right, let's stop here. And so the next one I'm going to go to is we have to go to 4. Let's go to 4. Any questions so far? Right, let's go to 4. Electron domains. 4 electron domains. And so my example is going to be carbon, right? Because carbon bonds to 4 things. And so let's do CH4, very common. Methane, right? This is like just comes out of the ground. It comes out of the ground in the Middle East and it's a gas. And so it just comes out of those oil wells and they can't utilize it, right? Because it's a gas. And so they just burn it. They just burn the methane. Right? But if you're close to the methane source, it's a very good source of fuel. But the problem is it's a gas, so it's hard to deal with because it takes up too much space. It takes up too much volume. So it's just not practical to ship because it takes up too much space. But if you're close to the source, then it's usable. It's just not practical if it's all the way in the middle of a desert somewhere. All right. So I did my skeletal structure. Valence electrons, carbon is 4, 4 hydrogens is 4. We have 8 valence electrons, single bonds. And so there's methane. Everything has an octet. This is a good model. Now for the VSEPR theory, how do 4 things get as far away from each other as possible? Now we have to get into 3 dimensions. Right now we have to get into 3 dimensions because in just 2 dimensions, these would be 90 degrees, right? And can they get further away than 90 degrees? They can in 3 dimensions. So in 3 dimensions, it's kind of hard to show. But it's typically drawn. Actually, I'm just going to jump right to the model, right? I'm going to jump right to that model to show you because the model is really cool. It's much better. And let's go to the model and we'll take away that lone pair. We'll add 1 bond, and we add 1 more bond. Look, so see, it's all on the same plane now. Now we take on 3 dimensions. And so you switch this thing around. So all these are equivalent, like all these bonds are equivalent. Like you can see like that, they're like, if I face it this way, there's 2 kind of coming towards us and then 2 going away from us, right? These 2 are kind of coming at us and there's 2 going away from us. The way we typically draw this, because now we're going to have to learn how to draw things in 3 dimensions. And so when it's typically drawn, this is kind of cool view, right? There's 1 coming straight at us. It's eclipsing the central atom. And then you can see the other 3 are kind of going away from the plane. And they're kind of like in a what's the word? A tripod. kind of like forming a tripod. But the way this is typically drawn is you want to put as many in the same plane as possible. So I'm going to put the one in front, the one going up in the same plane. So I could just, when I draw it, I could just draw it as a line. And then I'm going to put this one on the left in the same plane as well. What? It's all crooked. All right, I think that's right. Kind of, it's kind of bent a little bit. All right, I think these are in the same plane, but no, I want it this way. All right, here we go. It's hard to maneuver these things. All right, so I think the one going up and the one on the left are in the same plane. All right, so we have 1, 2, 3 atoms all in the same plane. So I could draw that. I could draw that just a central atom. So that'd be my carbon. And then one going up, that's just the line. And then there's a hydrogen. And kind of going off to the side. So it's not 90 degrees. It's like 110 degrees. 109.5. Don't forget that. 109.5. So, and then this one, these two are on the other side. But one's coming towards you and one's going away from you. And so we're going to draw that. And so how do we draw that? We employ the dash and the wedge. And so I'm going to draw the one going up, just it's in the same plane. So I just use a line. And then there's one coming down at like 110 degrees, 109.5. And so I draw those two. And then on the right side, if you remember, there's two that are kind of eclipsed. Like you can see the front one, you can't see the back one too much. And so what we're going to use the wedge as an artistic device to show that that is coming out of the plane of the page. So that wedge indicates it's coming out of the plane. Out of plane, the plane of the page, or the out of the page, out of the plane. There we go. There's no dot. So the wedge is coming out of the plane, and then we're going to use the dash. And we kind of put them close to each other because they're always eclipsed. The dash is going behind the page, or like, so this is coming towards you, and this one's going to like behind the plane. Or let's use into the plane. So out of the plane and into the plane. Or I guess behind is better. Into plane is probably more precise language. All right, so this is how we draw three dimensionals. So these guys are, but all the bond angles, all of them, no matter which bonds I choose, they're all 109.5. They're all equivalent. Right, they're all equivalent. And so we use the wedge and the dash, and the wedge and the dash are always eclipsed. When you draw the wedge and the dash, you always draw them eclipsed. And so this is how we're drawing in 3 dimensions. All right, so what do they call that shape? This shape is called a tetrahedron. Tetrahedral. And like I said, if you blow up balloons, this is a natural shape. If you blow up 4 balloons and you put them together, connect them, and they're all the same shape, they're going to take on this tetrahedral shape. They're going to point towards the corners of a tetrahedron. I was going to try to draw a tetrahedron, but I'm not going to. So if you have 4 electron domains, then they will take on this tetrahedral shape. And carbon, right? We're carbon-based. Most biological things are made with carbon because carbon's a unique atom. It's the only atom that bonds to itself over and over and over and over again. And carbon bonds to 4 things. So you're going to see this tetrahedral shape all the time. So you should memorize this bond angle, 109.5. So if you have 4 things, it's going to be tetrahedral. It'll have a 109.5 will be its bond angles. Any questions? All right, let's look at some of the derivatives of the 4 electron domains. And so some derivatives of 4 electron domains include ammonia. NH3, if you do the Lewis dot structure, I'm gonna put nitrogen in the middle. And prove it to yourself. Like, I guess I'll do it right. I could do it fast. Nitrogen has 5 valence electrons, 3 hydrogens is 3. So that's 8 valence electrons. So make the single bonds and then complete the octets. And so there you have. So we have 4 electron domains. So electron geometry is tetrahedral, right? Because there's 4 electron domains. You have 1 lone pair and 3 bonding domains, right? So 3 bonding domains. And so how would I draw that? So so the electron geometry is tetrahedral. I'm gonna draw it just the same way I drew my methane. Instead of using a CH bond, I'm just gonna put this one going up, right? To me, that's the easiest way to show it. So that would be my bond going up, right? So I'm gonna draw it in the tetrahedral fashion. Here's my one coming off at 100 and about 10 degrees, 109.5. And then on this side, I'll have one coming towards you and one going away from you. All right, and so so it takes on the same tetrahedral electron geometry because there's 4 electron domains. There's 3 bonding and 1 lone pair. So there are 4 electron domains. Or if you don't like long phrases, you could just say 4 groups, 4 electron groups. And so, but what is the shape? What is the molecular shape or electron or molecular geometry? I don't know. I like shape. It's one syllable. Electron shape. It's now we're just looking at these 3, and so these 3. I mean, these 1, 2, 3. These 4. We're looking at these 4. We're ignoring the lone pair, and so the shape is not tetrahedral anymore. Now the shape is it's trigonal. They're calling it trigonal. And it kind of looks like a pyramid. Trigonal pyramidal. Trigonal pyramidal is the shape of ammonia. Any questions? What are the bond angles? Well, you guys know the bond angles. They're not going to be 109.5 anymore, right? Because now we have this lone pair, which takes up too much. It takes up too much space. So the bond angle is going to be less than 109.5. I think it moves down by like 1.5, so it's probably like 108. But if you say less than, I know that you know what you're talking about. Less than 109.5. Any questions? Another derivative of the tetrahedral is going to be H2O. H2O, I think we did water already, right? But we don't know the shape of water. They did a whole movie about it. I don't think they talked about the chemistry really. What is the shape of water? And so the shape of water, so, right, we threw this together already. We did this, but there's 4 electron domains. There's 2 bonding domains and 2 lone pairs. And so it's going to take on that tetrahedral electron geometry. It's going to be tetrahedral because there's 4, right? Tetra meaning 4, and hedral means faces. So if you make a model, we can count the 4 faces. Maybe we could look at it. And so water. So how do we do it? So there's options here. I'm going to put 1 hydrogen up and 1 hydrogen there. And then you just got to use your imagination. That one's coming towards you and that one's going away from you, right? So, but I don't care, right? Because I'm not concerned about the lone pairs because I'm concerned, I already know the electron geometry. What is the molecular shape? What is the molecular shape? The molecular shape is going to be, well, it just looks like, it almost looks the same as that ozone, doesn't it? If we go backwards, The O's, it kind of looks, look at that. What's that shape? It's going to be bent. So that shape, molecular shape, is going to be bent. So what is the shape of water, right? You don't have to watch the movie. The shape of water is bent. What are the bond angles? What are the bond angles? Well, now we have two lone pairs, right? So now there's two lone pairs, and so they need even more room. And so the bond angles are going to be less than 109.5, and probably even more so than the ammonia, right? What did we say? The ammonia might have went, I think it goes down 1.5 each time. So if this went down to like 108, then I could do math, right? But I don't care if you can't do the math. Less than 109.5 is good. What is that? 106.5 probably is what they'd say. It sounds like a radio station. 106.5. Any questions? All right, so I kind of want to go backwards, and I have this blank page here. And so when I go backwards, I want to talk about this thing called polarity. Polarity. So we've looked at electronegativity values and dipoles. But now we have to kind of apply those dipoles. Dipoles are vectors. And what does it mean to be a vector? A vector has a magnitude. If you took physics, they teach you this. It has, so a vector, a dipole is a vector. It has a magnitude and it has a direction. So it's not just a magnitude. It also has a direction. And so we've looked at the polarity, right? If you were in my lecture, we looked at HF, and we saw that fluorine is a lot more electronegative than hydrogen. And so as a consequence, you get this dipole. And so the fluorine is more electronegative and the hydrogen is more electropositive. So that's one notation that you can use. You could also use this notation here. You could use the partial negative and partial positive, two notations that are used to show dipoles. Now, what if we have a molecule like, let's look at a cool molecule like carbon dioxide. Now, carbon dioxide is, if we do the Lewis dot structure, well, I'm going to put carbon in the middle because it bonds to four things. This is the thing that the plants use, right? Plants use this to make more food. They turn the carbon into sugar, and then they give us back the oxygen, which is good because we breathe the oxygen, and we burn our food with it. So carbon has 4, and 2 oxygens is 12. So we have 16 valence electrons. Make the single bonds 1, 2. Complete the octets. Oh no, I've already run out. So there's 8. Wait, 9. Wait, no, here I go. Oh, yeah. There we go. All right, 16. So is it done? No, carbon only has 4. Carbon only has 4. So I used 16, but I ran out of electrons. I can't complete the octets on the carbon, so I'll make a double bond over here, right? So, and then I'll make another double bond over here. All right, so now I've used all 16, 2, 4, 6, 8, 10, 12, 14, 16. Everything has a complete octet. So what is if we're looking at the essential carbon, I'm going to clean it up a little. So what is the shape? Well, there are two electron domains, right? So 2 electron domains. And so we know if there are 2 things, right? The electron geometry is linear, right? Because there's 2 things, right? And there's no lone pairs, and so the shape is also linear. But why do I bring this up? I brought this up because we're talking about polarity. So let's check it out again. Let's look at this molecule. So CO2 is, there's if we look at this, the carbon oxygen bond, we know that Oxygen is more electronegative than carbon, right? Oxygen has electronegativity, I think it's 3.5. And carbon has electronegativity 2.5. And so that's a difference of 1. And so you can definitely see that there's going to be a dipole going from left to right. But then if we look at the other bond, right? If we look at the other bond, so there's a magnitude and a direction. If we look at the other bond, so those electrons are pulled towards the right. Those shared electrons, those ones right there, they're pulled towards the right, towards oxygen. And then these shared electrons, these are also going to be pulled towards the right, towards oxygen. But you can see that the direction, since the shape is linear, right? These are 180 degrees apart. The direction of these dipoles are completely opposite. So these dipoles actually cancel because they're pulling in equal and opposite directions. Dipoles cancel because they are pulling equally in opposite directions. And so as a result, even though it has a local dipole, as a result, CO2 is non-polar. And we see in like when things are polar, right? So when things are polar, they're sticky, right? So HF is going to be attracted to another HF molecule, right? They're going to stick together because the opposite ends, the opposite charges are going to stick, right? So these are sticky. They stick together. They kind of form like attractive. So sticky meaning they have attractions. So they have attractive forces. And so what do we know about CO2? So we know that CO2 weighs, it's nonpolar. It weighs about 44 atomic mass units. So it's pretty heavy, right? But it's a gas, right? At room temperature, CO2 is a gas. And why is it a gas? Because the molecules are not attracted to one another, right? They're not sticky. They're not sticky because they're not attracted to one another. So if we go backwards, I'm going to take this concept of the polarity and I'm going to go backwards and look at, if we look at BF3, fluorine is definitely a lot more electronegative than boron, right? It's like 4.0, and I think boron is 2.0. So that's a huge dipole. That's a huge dipole. But because of the high symmetry of this trigonal planar arrangement, those three dipoles are going to cancel. Don't forget to put the tail on your dipole. I can't forget to put my tail. Oh, I didn't. All right, good. So since BF3, even though fluorine is a lot more electronegative than boron, these dipoles are going to cancel. You can look at it in the Cartesian coordinate system, right? This is pulling in the positive y, and these two are going to cancel in the negative y. And this is kind of pulling in the positive x, and this is going to cancel in the negative x. So BF3 is non-polar. It's non-polar because the dipoles cancel. And why do they cancel? Because they're pulling and they're canceling because of the high symmetry. So trigonal planar, what are the high symmetry groups? High symmetry, highly symmetrical molecules. They're going to be linear, is highly symmetrical. Trigonal planar. And tetrahedral. These are all highly symmetrical. And so if you have the same atoms attached to a highly symmetrical group like CO2 or BF3, or even if we go to here, well, CH bond is nonpolar anyway. But if I went to something like carbon tetrachloride, it would take on the same shape, and all those. This is nonpolar, even though chlorine is more electronegative. This is nonpolar because of the high symmetry. Dipoles cancel. Any questions? Let's apply this to ammonia. Let's apply our concept of polarity to ammonia. So now nitrogen is more electronegative than carbon, right? Nitrogen, I think, is like a 3.0 and hydrogen is a 2.1. And so there's definitely going to be a dipole there. And so each of these, there's going to be a dipole. And now this time, the dipole is not canceled by another hydrogen in this direction, right? So this is not highly symmetrical. Trigonal pyramidal is not highly symmetrical. And so there is going to be there's going to be a vector sum. The vector sum would be like going right through the center. So we could kind of see that this part of the molecule, the vector sum would be adding all those vectors together. And so you'll have the hydrogen end of the molecule as partially positive and the nitrogen end of the molecule as partially negative. So ammonia is polar. It's because it doesn't have that high symmetry anymore, right? It has a lone pair. So typically if you have one dipole in a molecule, it's going to be polar. And then if there's more than one dipole, you have to see if those dipoles cancel, see if they're highly symmetrical. Let's go to H2O. So we're checking out H2O, the shape of water. I guess we can extend this movie here. So oxygen is a lot more electronegative than hydrogen. Hydrogen is 2.1. Oxygen is 3.5. So it's definitely going to have a dipole, right? So it's going to point in that direction. And then there's one pointing in this direction. And this is not linear, right? This is bent. This is bent. And so they're not going to cancel. So they'll kind of cancel in the y direction, right? But they're gonna be additive in the positive x direction. They're kind of additive. Well, the shape of my molecule is crazy. But you can see that there's a vector sum that'll kind of point right through the molecule. So the vector sum will kind of be like from here to here. That'd be the vector sum. And so water is polar. It has a positive end and a negative end. So the oxygen is partially negative and the hydrogens are partially positive, right? So you have like this positive end and a negative end. So water is a polar molecule. And so what is that? What is the consequence of that? Well, we said polar things are sticky, right? So water molecules, they stick together, right? That's how the water can get from the roots of a tree all the way up to the leaves, right? Because water molecules are going to stick together. They're going to stick together. And so we can analyze this. If we look at what do we know about water, H2O, it weighs about 18 atomic mass units. And what is its state? It is a liquid. Why is it a liquid? Why is this a liquid? It weighs 18, and carbon dioxide is a gas, and it weighs more than twice as much, right? Carbon dioxide weighs more than twice as much, right? You would think it'd be like heavy and fall down, but it's a gas because it's not attractive, right? Think about what a gas is. Gas means the particles are far apart from one another, right? They're not close together. They're not in a condensed state. And so carbon dioxide is not in a condensed state because it is non-polar. There's no attraction. There's very little attraction between carbon dioxide molecules, yet a lighter molecule like water only weighs like 18, but this is a liquid because there are attractions. These are attractive forces. And so that's why water is, so molecular shape, the VSEPR theory, able to predict molecular shapes, very important, very, very important for understanding molecules. Any questions? So when soap disrupts surface tension in water, it's interfering with polars. Exactly. Yeah. So when the soap upsets the the attractive forces. These are water has very strong attractive forces. They're called hydrogen bonds. It's the same thing that holds like your DNA strands together. They're very attractive. If you take biology, they'll call them very weak because they're attractive forces, and attractive forces are by definition weak, right? They're not the same as bonds. So it's a misnomer to call them hydrogen bonds. They're not really bonds, but they're attractive forces. And And so when you disrupt those attractive forces by putting some oil or putting like soap in there, like I used to do this demo when I taught Chem 100, where we would put like pepper on the surface of water, and then you put some soap in, and you can see it all. It just like falls down. Good point. All right, let's see if we can apply these ideas to your lab. Right. So I think we've covered a lot, right? We've covered a lot. We covered these shapes, how to go about getting these shapes. Let's go back and look at this thing. This is kind of cool, right? So we have this. Let's go with the real one. Let's go back to the real one. Let's not get away from the shape one. So BF3, we did CO2, we did linear. There's no, so we're making them real. BF3, CO2, ammonia, right? So we did ammonia. Let's flip ammonia around, and you can see the bond angles, right? It's less than 109.5. So how do you draw it? I drew it this way, right? So you can see tetrahedral and trigonal pyramid is the shape. Here's ammonia. Let's look at water. We just did water, and so water is even less. And so those are lone pairs. So how did I draw my water? I drew my water like this. I think that's the best way to draw it, right? It's the cleanest. But there are options as far as drawing it. Notice that all those bonds are identical. So water is bent. And it doesn't talk about polarity, but water is also polar, right? You can see it from the shape, right? Because from the shape, once you get away from that highly symmetrical shape, then the bonds can start to, once you go away from that symmetry, then you can introduce dipoles and stuff. The dipoles are no longer going to cancel. What else do we have? CH4 we did, right? We did CH4, 109.5. Everything is the same. I don't like any more of those. All right, let's go look at your lab. Here it is. And so this kind of shows you the steric number refers to the bonding domains. Steric number refers to bonding domains. And so these are all bonds, right? Steric numbers. So they refer to bonds. So if you have 2 bonds, linear, 3 bonds, trigonal planar. If you have a lone pair, if one of those bonding domains is a lone pair, it's bent, right? That we saw that was ozone. And then here we have, this would be methane, tetrahedral, 4 bonding domains. If one of them is a lone pair, this would be like your ammonia. Then it's trigonal planar. So they're putting the E as a lone pair and they're putting them on a stick, which I don't like. I don't like putting the electrons on a stick. And then this one, it would be your water, right? So this is your water with 2 lone pairs and it's bent. All right, now they're going down further. They're going to 5 bonding domains and 6 bonding domains. And so you might be thinking, wait a minute, these are guys going to upset, they're going to exceed the octet rule. And yes, they do. So now we have to go back to octet rule violators. So there are more octet rule violators. So we saw the too few, right? So octet rule violators, too few. We saw beryllium and boron, and you could put aluminum in there. But now you can have too many. And so the way they explain the too many is that in the third, so we have N equals 1, right? You have hydrogen and you have helium. N equals 2, you have the S and the P's. Right, so this would go from, so N equals 2 will take you from lithium all the way to neon. So N equals 3. In the third energy level, you have your S, P's, and D's. And so we're talking about non-metals, right? Because we're talking about molecules. So we're concerned about molecules. And so if we look at a periodic table, Do I need to look at a periodic table? So I think I could do this without. So we have like our sodium and magnesium, if I'm not mistaken, and then aluminum, right? So that's still metal. But then you're getting to silicon, right? And then after silicon is phosphorus, and then chlorine, chlorine, and then argon. And so even though these all have, these are the P's, right? These are the P's. They have access to these. Why did I put an S there? Why is there an S? They have access to these D's because it's in their shell. So these D's are empty. They're empty, but accessible. And so we're going to use this explanation to kind of understand why we can have things like PCl5. Because once you get into this third shell, right, once you get to phosphorus, it's pretty much phosphorus and higher, although I feel like there should be an example with silicon, right? But maybe not. So phosphorus and higher, once you get to phosphorus and higher, too many phosphorus and higher atomic numbers. They can exceed the octet rule. And so we have something like PCl3, PCl5. There's PCl3 and there's PCl5. PCl5, let's do the Lewis dot structure. I'm going to put phosphorus in the middle. But now it's just like, I'm just arranging it this way because I know how to arrange them. And then we count lone pairs. Phosphorus has 5. And then 5 chlorines is 5 times 7 is 35. 40 valence electrons. 1, 2, 3, 4, 5. I use 10. I have 30 left. Complete the octets. There you have it. There you have it. Everything has an octet except for phosphorus. Phosphorus has 10. 10 electrons are on it, right? Because it's an octet rule violator. It has too many. And they say it can because it has access to those Ds. It has access to those D orbitals. And then is it polar or non-polar? Well, this is actually a highly symmetrical geometry. What does that geometry look like? Let's jump to the we're going to this one. PCl5, there it is. And this is one of, so 5 things, no lone pairs. And it kind of has like an axis, like you have these atoms that are up and down in the axial position. They're kind of 180 degrees apart. And then you have these 3 in the equatorial position, and those are 120 degrees apart. So there's actually, I wonder if we can see that 120. There we go. So you have 90 degrees and then 120. So it's kind of like it's almost like a linear molecule combined with a trigonal planar molecule. So it's like almost like a linear and a trigonal planar. So you have these things that are in the equatorial. You have the 3 that are in the equatorial position, like the equator, and those are 120 degrees apart. And then you have these 2 that are what they call axial, and those are 180 degrees apart, but they're 90 degrees from the equator, right? So they're 90 degrees from the equator. So you have 2 different types of bonds, right? You have 2 different types of bonds. You have 180 and 90. And so they call this trigonal bipyramidal. So it's like 2 of the ammonia molecules stuck together, if you will. Trigonal bipyramidal. How do you draw it? How are we going to draw it? You could draw it just like we draw. So I'll put as many in the plane as possible. So I put 3 in the plane, like making a T there, and then 1 coming at you and 1 going away from you. So let's draw that. So let's draw it. So I'm going to draw it in 3 dimensions. There's 1 up. There's 1. These are all in the plane. CL. And again, I don't care about the lone pairs on the atoms on the outside. For if you're doing a Lewis dot, you have to include all the dots because it's in the word Lewis dot. So there's your Lewis dot. But when you're doing your 3D, right, we're just concerned about the central atom. And so you don't have to put the dots on the on the outer atoms. So this one's coming towards you and this one's going away from you. Could there be resonance structures for it since the angles aren't the same? Resonance structures refer to when we're moving electrons. Resonance structures refer to typically when you're just moving double bond electrons. Pretty much is when you're so it's moving the electrons, and so these are all single bonds. So you're not going to have any resonance structures. No need for resonance structures, right? Everything has an octet. The angles are locked in place, right? And since these angles are locked in place, 120 and 90, right? So these are like 120, and so those are how do I show? So these two are 120. Those are 120, and then these are 90. So this one has 2 bond angles. And then chlorine is a lot more electronegative than phosphorus. I don't know the numbers off the top of my head. So chlorine, I think, is 3.0. What is phosphorus? I could guess it. Maybe it's 2.1. I'm not sure. That's a guess. But chlorine is a lot more electronegative than phosphorus. And so you're going to have all these local dipoles, right? So you're going to have all these local dipoles. But this is highly symmetrical. This is one of those highly symmetrical shapes. If you take 5 balloons and you blow them up to the same size and you connect them at the center, they will take on this shape. They will take on this trigonal bipyramidal shape. And so this would be the electron geometry and the molecular shape. Trigonal bipyramidal. And so this is non-polar because of the high symmetry. This is one of those high symmetry groups. So since all these atoms are the same, they're going to cancel, right? Because the dipoles cancel. So all those dipoles are going to cancel. So that's why it's not polar. All right, so now you can imagine, right? Just like we had with we had tetrahedral, and then we started putting lone pairs in and getting derivatives, right? So we had our trigonal pyramidal, that was tetrahedral electron geometry, and we had the bent, right? We had bent, water was bent. And so you can imagine the same thing is going to apply for our trigonal bipyramidal. If we start pulling these off and putting lone pairs in, we're going to have examples of derivative geometry, derivative shapes. We're going to have derivative shapes. And kind of, I'm going to have to go through all of this in lecture on Monday. I guess we could do it here. So let's look at some of these derivative shapes. I don't have my notes with me, but right. So we're going to have, we'll go through the model. We'll go through the model for these derivative shapes. That's a good idea. All right, so we have so if we have 5 things, let's go back to the model. We're going to model. We're going to go with 5 things. There's our trigonal bipyramidal. Let's take one off and add a lone pair. Now, what is the shape? The shape is a seesaw. The shape is a seesaw. Right, you guys, do you guys know what a seesaw is? I know there's one there. There used to be one above the park in Punahou, above Punahou, there's a park, and I saw a seesaw. That was a long time ago. That was when my daughter's 21 now, so it's a long time since I've been there. Maybe it's not there anymore. Right, but you guys see what a seesaw is, right? So somebody sits on this end and it goes down, and someone sits on that end and it goes on. So, but if so, this is a derivative shape. If we remove a lone pair, if we remove a bond and replace it with a lone pair, I need an example of this. We get a seesaw shape. And so why does the lone pair go in the equatorial position and not in the axial position, right? Why does the lone pair going to go in the equatorial position and not in the axial position? And it's because if we put it in the axial position, there would be repulsions. There would be three. So let's picture it. I'm going to have to draw it. So when making a seesaw, I think I have an example of a seesaw. Dun, 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 dun. I may have to refer to I'll have to refer to, no, not there. Boom, this one. I need an example of a seesaw. SF4. I think SF4 will do it for us. Let's do SF4. All right, we'll do this one together. Let's do it in this color. SF4. I'm going to put S in the center because fluorine only bonds one thing, right? SF4. And you might want to arrange it like this, right? That looks good. Sulfur has same as oxygen, 6. 3 fluorines is, no, that's 4 fluorines. 4 fluorines is 28. So we have 34 valence electrons. Make the bonds. That's 8. Complete the octets. And then, so I've used 8 times 4 is 32. I have 2 more electrons. Where am I going to put it? I'm going to put it on that central. That's the only place I can put it, right? Because this is the only thing that can exceed the octet rule, right? Because phosphorus and higher. So that guy, now that guy has 10 electrons around it. It's an octet rule violator. It's exceeding the octet rule. What is the shape, right? So there's 5 electron domains. And so we know the electron geometry is going to be trigonal bipyramidal. Trigonal bipyramidal. But what is the shape of this thing? And so where do we put that lone pair? That was the question, right? Where do we put the lone pair? Let me take this 1 second. I'll be right there. Hello? This is Kevin. Good afternoon. All right, sorry about that. I had to take that call. Let's see where we were. We were looking at all right, so why why does the lone pair, right? There's a couple of options where we can put this lone pair, right? We could put it in the axial position, or we could put it in the equatorial position, right? So if I put it, let's first, the computer kind of showed us where it went already, right? But if I put it in this position, if I put it in that position, what's going to happen is that there are 3 repulsions that are 90 degrees apart, right? So if I put it here, there are 3 90-degree repulsions with the bonding electrons, right? And so it's, in the chemistry, you'll see that things always go to the lowest energy. It's just the natural phenomenon. The lowest energy situation will always occur, almost always. Can't say always. But so if I put it in the equatorial position, I'll put it like so. Keep that guy here. If I put the lone pair in the equatorial position, now there are only two 90-degree repulsions. And so it'll go, and so that's why it takes this shape. So that's why this is the preferred shape. This shape takes place, and this shape does not happen. And so there you get the seesaw. So the shape of this is going to be seesaw. And what are your bond angles? Well, again, the lone pair is going, so normally we had 120 and 90. And so now the bond angles are going to be less than 120 and less than 90 degrees. Right, because they're going to take, these guys take more space. Any questions? All right, so so there are going to be other derivatives as well, right? So you're going to have another example where you have, so this was so we just saw trigonal. I think it's lawyers. Everything's because of lawyers suing and stuff. When I was a kid, they tried to ban surfing. I grew up in New York. It's all lawyers. The was that a direct question, or was that, everyone saw that? If somebody asked why are the seesaws disappearing? All right. So trigonal bipyramidal. So this would be this would be 5 electron domains. And so this would be the electron geometry. If you go to the molecular shape, so 5 electron domains is going to be, again, trigonal bipyramidal. But if you go to like 4 bonding and 1 lone pair, then the shape changes to seesaw. If you go to 3 and 2, then the shape's going to change again, and you'll see that you're going to get like a T shape. You'll get a T shape. So you guys could prove that to yourself, do those examples. And so that'd be 3 bonding and 2 lone pairs. So you're always going to have 5 electron domains. 5 electron domains, electron geometry doesn't change. The molecular shape changes. I think you can go all the way down to 2 and 3, and then it becomes linear. And so you can see that, like, if you have all the same things, right, like the PCl5, it's going to be nonpolar. As soon as you start to get like these T shapes and the seesaws, now you can see that this is going to be polar, right? Because now you don't have that extra, because the fluorine is more electronegative than the sulfur. So you'll have these dipoles. And so this is no longer highly symmetrical. And so this is going to be polar. You're not having that other bond canceling. So as soon as you go to these, if you go away, once you go to these derivatives, you're going to start to get possibility of polarity. And linear probably is going to be, you know, you're back to a symmetrical structure. All right, the last one, any questions? The last, what did I stop share for? Sometimes I hit the wrong buttons. The last one is 6 electron domains, and that is going to be what's known as octahedral. It has 8 faces. Octahedral has 8 faces, and everything is 90 degrees apart. What's an example? I think it's SF6. So an example would be SF6. And so you'll end up with, if we do SF6, you'll have SFF. I'm going right to the 3-dimensional structure. SF6, and so you can see that this is going to be an octet rule violator that has 12 electrons around it for that center. So it can exceed the octet rule. And this is going to be nonpolar, right? Because this is highly symmetrical. And the bond angles are 90 degrees. Everything is 90 degrees apart. So bond angles are 90 degrees. And then you'll have derivatives, right? You could have 5 and 1, and 5 and 1, you just take one away, and it doesn't matter which one because they're all equivalent. If you take one away, then the shape goes from the electron geometry, the shape becomes a square pyramid. And if you take 2 away, then it'll go to 4 and 2, and this is where we stop. And so at 4 and 2, it becomes so square pyramid, that would tend to be polar, right? Because you're just missing like the bottom, right? You're missing that bottom. And then if you go to 4 and 2, then you're going to go into what's called a square planar. Square planar is interesting geometry. You see in transition metals, they take on the square planar geometry. And typically the square planar, it's going back to being highly symmetrical. So like a square planar can be very symmetrical. So because you just have 4 things in the same plane. And so this could be non-polar depending on what you have there. And those are all the geometries. So you have the 5 major geometries, which are linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. And then you have your derivative shapes. If there's lone pairs, right? If you have lone pairs, then you have derivative shapes. And now the book kind of talks about this thing, not the book, the lab. I think we covered almost everything. Bond angles, not the only thing we didn't cover is hybridization. And so you get to the concept of hybridization in chapter 8. They introduced the concept of hybridization, and it comes out of valence bond theory. And I'm not going to teach valence bond theory here, but I'll try to hit it on Monday. So it's a nice theory. It goes right along with our Lewis structures. It just says that the bonds are formed from the overlap of atomic orbitals. That's all it's saying, is that the bonds are formed from the overlap of atomic orbitals. Maybe I'll touch on it a little bit. All right, let me touch on it a little bit. So valence bond theory says that bonds are formed when atomic orbitals overlap, right? And so we can see like hydrogen. Hydrogen has a 1s orbital and another hydrogen. Here's another 1s orbital. And so where they overlap, that's the bond. That's where the electrons are. So that's your bond. overlap. So that bond overlap, the overlap of atomic orbitals. One S, right? That's a 1s. And so the bond is the overlap of atomic orbitals. And so when you get to, so that's fine, right? So there's a bond formed between two 1s orbitals. And then the problem lies when we take like carbon. And so carbon has an s orbital and 3 p orbitals. And there's 4 electrons, right? It has 4 electrons, and we know we fill it up this way, right? And so based on the atomic orbital picture, the atomic orbital diagram of carbon, this atomic orbital diagram doesn't really explain why we have methane having 4 equivalent bonds, arranged in this arrangement because, right, so if you have an s orbital, and you guys remember the p orbitals, right, they're like 90 degrees apart. Right, so that doesn't, so this bonding picture, if I put the electrons, so here's my nucleus, right? And so if I put a 1s orbital and then a couple of p orbitals for my picture of carbon, right? This is my carbon picture, and I left one of the p orbitals out, right, because it's not filled. And so I could put 2 electrons, let's put some like pink electrons in there. So there's 2 electrons in an s, and there's 1 electron in each of these p's. And so the only place you can really form bonds, right, is with hydrogen 1s. So here would be a 1s orbital of hydrogen, and you can form this bond. But this doesn't look anything like what the real methane molecule looks like. So this methane molecule, like if it followed the atomic orbital diagram of carbon, you would have like a carbon and then a hydrogen, and these guys would be 90 degrees apart. And then there'd be a lone pair, right? But that's not methane. Methane doesn't look like that at all, right? So what's going on? How do we explain this? So when you have a really good model, but it's really not matching your experimental, what's going on in reality, you have to tweak your model. You have to, and so they tweak the model, and it actually works. So it makes sense. Sometimes you have to scrap your model and throw it away and come up with a new model. But we can tweak it, and we can incorporate the concept of hybridization. So we can say what's happening when the atomic orbitals of carbon, when they start to form bonds, they're going to change. So this is the atomic orbitals, but when it forms a bond, it's going to change. When these hydrogens come close and they form bonds, and they're going to be hybridized. So we're going to hybridize them. And so we're going to hybridize these 4 atomic orbitals. And so we can see from this picture that we have 4 equivalent bonds. There are 4 equivalent bonds, and they're 109 degrees apart. And so we're going to take these 4 atomic orbitals, and we're going to hybridize them, and we're going to create 4 equivalent hybrid orbitals. So we took an s and we took 3 p orbitals, and we kind of put them together, and they put their energies and shapes together. And so we came up with 4 sp3 hybrid orbitals, all of the same energy. So these are the sp3 hybrid orbitals. And so there's 4 electrons, we'll put an electron in each one. And these are mathematically generated using like some heavy calculus. And what do they look like? The sp3, so if you take an s and you take the 3 p's, s and these 3 p's, and you hybridize them, you come up with an sp3 hybrid orbital. And the sp3 hybrid orbital points, it has like a large lobe, which is directional, and a small lobe, and it points towards the corners of a tetrahedron. So these are sp3 hybrid orbitals. Those are in the same plane. This one's coming towards you, and this one is going away from you. And so these are the sp3 hybrid orbitals. And so now we have 4 equivalent orbitals, right? And that represents the bonding in methane. So how do we introduce the concept of hybridization? Well, it depends on how many orbitals, how many equivalent orbitals do you need? So if you have 4 electron domains, you're going to need 4 equivalent orbitals. And so you'll be sp3 hybridized. Does that make sense? So 4 electron domains is going to be, so what is the hybridization? Electron domains. For electron domains, it's the hybridization is going to be sp3 because you need 4 equivalent orbitals. All right, what if I only had 3 electron domains? If you have only 3 electron domains, then you only need 3 hybrid orbitals, right? So 3 hybrid orbitals, it'll be sp2. And so what are these bond angles? This is 109.5. sp2, we only need 3. This is 120. All right, what if I need 2? What about like something like, so this would explain, what about CO2? Only 2. CO2 is sp hybridized, and those electron domains are 180 degrees apart. All right, what about PCl5? PCl5 has 5 electron domains. 5 electron domains. Well, we noticed that these are the octet rule violators. So this is going to be sp3d. That's your 5th orbital, right? So you're going to take an S, 3 P's, and a D because you need 5 electron domains. We only have an S. We only had 4, so we need one more. We take a D. So you'll see this with phosphorus and higher. And what are those bond angles? Well, you'll have some at 90, and you'll have some at 120. Right, the same as your trigonal bipyramidal. What about 6 electron domains? 6 electron domains is going to be sp3d2. And that'll be your octahedral, right? And they're all 90 degrees. So this corresponds to your tetrahedral. This corresponds to your trigonal planar. This corresponds to linear. This corresponds to trigonal bipyramidal. And this corresponds to octahedral. And I'll try to hit this more in lecture as far as the hybridization. Let's do 3. I kind of want to explore 3. If we look at formaldehyde, let's look at formaldehyde. I like this example, H2CO, and I know what it looks like. I did this in my lecture. And so bonding, oxygen is 6, carbon is 4, 2 hydrogens is 2. That's 14 valence electrons. 1, 2, 3, complete the octets. Did I count right? That's 12. I can't count. That's 12. And then you see carbon needs 2 more, but I used all the electrons. So what do? I form a double bond. And so what does that picture look like? It's trigonal planar. Trigonal planar, right? 3 electron domains. There's 3 bonding domains, right? Double bond counts the same as a single bond. So we have 3 bonding domains. Trigonal planar. And we said the hybridization is sp2, right? Because you only need 3. And so let's look at that carbon again. So carbon has its S's and its 3 P's, but we only need to take an S and 2 of the P's to make these bond angles, right? So you only need to take an S to make these sp2 hybrid orbitals. Right, so these are my sp2 hybrid orbitals. They're directional, right? They have a big lobe and a little lobe. And so you can see these are forming these bonds, right? So we could put the hydrogen over here if you want, right? Over here, you could put the, I'm not going to put the hydrogen. Well, maybe I will. I don't want to mess up my molecule too much, right? But I guess we could put like, oh, I didn't want that color. You could put the hydrogen over on this side, right? It's going to overlap with that S, and the hydrogen over here on this side. And then you'd have what's going on with the oxygen. Well, the oxygen also has 3 electron domains, right? It has a bonding domain. So if we look at that oxygen, it has 3 domains as well. It has 1 bonding and 2 lone pairs. So it too, so the oxygen is also sp2 hybridized. So if we look at oxygen, it has an S, it has those 3 P's. So again, oxygen is sp2 hybridized. And so I'm going to show the overlap with the oxygen sp2 hybrid orbital, right? So there's that overlap. So there's the bond. And so whenever you have a bond between nuclei, so if the bond, the electrons are between nuclei, we call that a sigma bond. Sigma bond. And so most bonds are sigma bonds, right? So there's a sigma bond here, there's a sigma bond there. So there's 3 sigma bonds. But what's left over, right? So both, if we look here, we can see that there is a leftover P on the oxygen and there's a leftover P on the carbon. And so if I draw that leftover P, the P's are going, so here's my leftover P, and I have to kind of make it big. So there's my leftover P on my carbon, and here's, I didn't show those other two orbitals on oxygen, right? There's 3 of them, right? I guess I could show them. Not messing up my picture too much. So that's my sp2 hybrid orbitals. Right, so these are the lone pairs on the oxygen. And then my leftover P on carbon is in red, and I'll put my leftover P on oxygen in red. And p orbitals, they can overlap in a variety of ways, right? You can have p orbitals overlap in a sigma fashion, right? So if those are the nuclei, right? The electron density, that'd be a sigma bond. But p's can also overlap so that their lobes, they overlap in this fashion, right? And so this would be your internuclear, this is your nuclei here. And so these electrons are above and below the plane. And so we call that a pi bond. And so when electrons are, this is a bond, electrons are above and below internuclear axis, we refer to that as a pi bond. And so it's hard to show, but these electrons here, these p orbitals, they are overlapping in a pi fashion. So when you have a double bond, right? Because you can only have there's only room for one sigma bond. There's only room. So we have one sigma bond between the carbon and the oxygen, but where's that second bond going to be, right? The second bond has to be somewhere else. And the second bond is the pi bond. So if you have a double bond, you have one sigma and one pi. One sigma and one pi. Whoa, crazy. Valence bond theory. Any questions? I think that covers everything. I taught the, right, so we got hybridization, shape, polar, nonpolar, bond angles, Lewis structure. I think you guys can do all this now. Right, you know how to apply the negative charge. I covered that in lecture. And this model is it's a good cheat, right? It almost has everything here. So if we switch back to real molecules, and then you can just go through. Too bad there's no like xenon difluoride. This is linear. BF3 we did CLF. So a lot of the answers are in here. It's going to be a seesaw. No, this is a T-shape, right? This is your T-shape. NH3 we did. SF4. SF4 is interesting. Check out SF4. Seesaw. Oh, we did that one though. Xenon. What is xenon? Xenon is forming bonds. Crazy. Yes. So this is a square planar. Bromine difluoride. What is this thing? Square pyramidal. What is our square pyramid? That's kind of cool. PCl5 we did, SF6 we did. Any questions? All right. Have a great Thursday. Be well. You're welcome.
Thank you, Professor.
You're welcome.